Hi folks, we are on the Unit 2, Day 2, and this is video number 2. So we're just going to continue, and the second example I have is a little bit different than planes. Really the other thing that we can have here is with boats in water currents. They work very much the same as planes being kind of pushed to one direction or another, faster or slower with the wind. Likewise, you would have a boat that kind of had its own direction and had its own velocity, but depending how the water around it was moving, you may end up going a slightly different direction or faster or slower. So kind of the equivalent in this one to saying plane plus the wind equals the resultant. Here I'm going to say boat plus the current equals the resultant. It's going to work really the same way. So the first question here says a canoeist can paddle at a speed of 5 kilometers per hour in still water. So this in still water, that means that's the boat speed or boat velocity with no current. That means that that's the boat's velocity, not the resultant velocity. She wishes to cross a 400 meter wide river that has a current of 2 kilometers per hour. So the first question, if she steers her canoe perpendicular to the current, determine a resultant velocity. So the first situation, she's trying to go across a river, and if she goes perpendicular to the current, we want to find what the resultant would be. Now, one really important thing, current is always parallel to the sides of a river. Now, in real life, that's obviously maybe not quite true. There could be, different factors in the river that might affect the current kind of going in slightly different directions. But we're going to assume, in general, if you have a river, that you've got a current going in one direction. So that we're going to have, there's our river, and we're going to have a current vector going downstream. That's another kind of term that we use. The direction the current is going, we're going to call downstream. And then upstream would be the other word from where the current comes from. So if the current goes left to right, the left part would be the upstream, or the right hand part where the current's going towards is downstream. So if I said, for instance, she aimed her canoe 20 degrees upstream, that would be from here, she's pointing towards upstream by an angle of 20 degrees. But that's not what this question says. This one says that she's going to steer her canoe perpendicular to the current. So she's just pointing right at the opposite bank and going that direction. And I always use B for boat, even if it's a canoe, because then I don't get mixed up with a C for canoe and C for current. So I'm going boat and current, and then we're going to figure out what our resultant is. So here I have the velocity of the boat. I feel like current is water, so I'll make that blue. And then adding the current to it, I'm going to get a resultant velocity. So we need to figure out the magnitude and direction of that resultant. So we want to know how fast the canoe ends up moving, and we can tell for sure that it's going to be faster than the 5 kilometers an hour she can actually paddle without a current, and also what direction she ends up going in. So here, because this is perpendicular, we've got a nice right-hand triangle. So the magnitude of the resultant, just Pythagorean theorem here, I don't even need trig, is the square root of 5 squared plus 2 squared. Oh, I should have just used a calculator because it's a velocity. Square root of 29 is 5.39. Obviously, we don't want to leave exact value answers if it is a real life question. Nobody would say, oh, I paddled route 29 kilometers an hour. Give an actual number. Then we also need to figure out what the angle that she traveled was. So I'm going to put a little theta in there. And you know what? I think I'm going to use tan just so I don't have to use like the rounded off one there. I'm going to say tan theta is the current is 2 over the boats is 5. And that gives me a value of 21.80 degrees. So I've gotten my angle for theta. So we would put a statement saying that the resultant velocity is 5.39 kilometers per hour, and it's 21.8 degrees downstream. That's the direction she's going. So we can assume kind of from a perpendicular, it's angled 21.8 degrees towards the downstream direction. We don't actually know what direction this river is going. It could be going the other way, in which case that would be downstream. So that upstream, downstream can be helpful in describing directions with currents. The next one asks us, how far down the river will the canoe land? So this has kind of come away from being a question about vectors to saying, well, okay, where is she going to actually end up? Now we've got, say this was her starting point. We know that from the perpendicular where she was aiming, she's actually going at an angle of 21.8 degrees. And it also, in the original question, told us that 400 meters is the width of the river. So we can figure out how far down the canoe will land, like how far down river. This would be X here. Okay, so then we've just got a tan ratio to find that in meters. So tan 21.8 degrees is X over 400. So we get 160 meters. So therefore she will land 160 meters downstream. So if she wanted to just get across the river, by aiming directly across, she's actually getting pushed pretty far out of the way because of that current. So what if that's not what she wanted? What if she wanted to just go straight across the river? What direction should she head from the start? So this is a different setup here. Let's say that's her starting point. Now we know that the current, I'm just going to put C off over there, because remember, vectors have magnitude, they have direction, but they don't have location. So I'm just putting my current there. We'll move it to where we need it for the vector addition later. Now, if she wants to go right across the river, that's actually the resultant. We want the resultant to go there. So with the current pushing her this direction, where would she have to aim? She would have to aim upstream and get pushed downstream. So she would have to have her velocity with the boat going that way and realize that this current is going to push her downstream. So this is a different kind of setup, isn't it? It's a little bit different of a diagram. So, and this can be a little bit confusing because we know the current is 2 kilometers per hour. We know her velocity is 5 in still water. So that would be the 5 now. The 5 isn't going straight across. She's going upstream. And then we get the magnitude of the resultant there. So here, the magnitude of the resultant is now not the hypotenuse. The resultant is on one of the legs of that right angle triangle. So it's the square root of 5 squared minus 2 squared. So the resultant is the square root of 21, not 29. So now the resultant's 4.58 kilometers per hour. And we want to know what direction she should have headed from the start. So we want to find that. We want to say what angle should she have headed upstream. And I guess we didn't need the resultant yet. That might be D. But we could use this. Now would be a sine ratio with opposite and hypotenuse. So we could say sine theta is 2 over 5. So theta is about 23.58. And that's not exactly, where's my other? That's not the same angle. A lot of people kind of say, oh, well, if you end up going that far downstream, shouldn't you just go that far upstream? But remember, this is not kind of a reflection, because if you're going upstream, it's not this resultant that was 5.39 on the hypotenuse. It's just your actual how fast you can paddle, which was just 5. So I think there's an instinct here to just say, oh, well, it would just be like flip the other side. But the whole dimensions of those triangles will change a little bit, or a lot, depending on how fast that river goes. So therefore, she should head 23.58 degrees upstream for a velocity of 4.58 kilometers per hour straight across. And I realize it didn't really ask for the velocity yet, but I think that that's the next question. Yeah. And there, what is her new speed crossing the river? Her new speed is 4.58 kilometers per hour. Apparently I should combine those two. So that's it for day 2. The next stuff we'll be moving into is a little bit more theoretical, but both of the velocity and forces are pretty straightforward applications of all of the same kinds of vector addition that we did in Unit 1. Moving along into day 3, we're going to be looking at some new kinds of operations we can do with geometric and then algebraic vectors.